Buenos dias, good morning. So we are having today the pleasure of hosting Juan Fuster and some colleagues from IFIC from Valencia. Juan got a PhD working at DESI some years ago, and then he has worked consistently at CERN and Valencia in all the different stages at CERN, for example, the Delphi experimental lab and Atlas. In the last years, Juan has been involved a lot in accelerator technologies and also in medical physics. They are now launching a very interesting project at Valencia, and I hope that he may comment sometime on this project. He has an impressive publication record. He has done policy and management responsibilities, and he received a few years ago the World Research Award. So I think it's a very good occasion to hear about things which are happening.
Thank you, Aston. So first of all, my talk will be about accelerators. As Aston said, is one of the last activities in which I am involved. I am not an expert on accelerators, but I'm trying to learn still. I think it helped. So I want to thank for the invitation and especially to Gaston, because it is also an opportunity for us as we are planning for making a new installation infrastructure in Valencia. It should be, similar or equivalent to the one you have here. We have many things to learn, as we are realizing, and I want to thank and acknowledge your advice and help. Also, I have to say that I have taken some ideas, and just when you're preparing such a talk, you take ideas, slides, and materials from quite many people. So here are the people whom I have been using some of the information. So first of all, I would like to start with what is the field of particle physics, why we are doing research on particle physics, and what are our motivations, our main purposes. So what is the purpose, the vision, method of the field? So first of all, what do we try? So we want to understand the fundamental nature and the structure of the energy, matter, space, and time, and apply this knowledge to understand better what is the origin, evolution, and fate of the universe. Of course, to make this possible, at the same time, we have to develop instruments that allow us to observe nature at the required scale and subsequently explore its most immediate applications for the society. So, first of all, what are the questions that we as a physicist ask ourselves usually? So, how did the universe begin? What is its fate? What is it made of? What are the fundamental laws? Why do we exist? Where do we come from? So, in this talk, I will not cover everything, but I will concentrate mainly on these three talks. What is the universe made of? What are the fundamental laws? And how do we exist? Or why do we exist? So first of all, let's start from the very beginning. Okay, and then we start from the Big Bang, which is 13.8 billion years ago, which is a day that had no yesterday. Right? And most of the pictures show that the Big Bang as a big explosion, but in fact, probably what it was very dark, because there was no light at that. I cannot even imagine how it was, but certainly without light. So how do we observe these first moments of the universe? So we try, with astronomy, we try to observe it with telescopes. But how far we can go with telescopes? So here you see an image from the early universe, which is today what has been possible to have an image, the shortest time from the very beginning of the universe, which is 13.1 billion, not 30.8, 30.1 billion. And this is, an image from the Webb Space Telescope, which tells us about this early universe, where already you can see the galaxies, which is how far we can go using images. So this is another image, from the Planck telescope, which is the closest we can go, on observation with telescope, which is around 1,300,000 years after the Big Bang. And that is an image of how the early universe was about. And that is the closest we can go using telescopes. So what happened in this early universe is that, here is the periodic table. How many you know about at that time? Which were the elements which were formed? The elements which were formed mainly was hydrogen and helium, nothing else. So where do the other elements come from? Where they are made? Where are produced? So they are produced in the stars. So yeah, well, the sentence by Carl Sagan, we are all stardust. So now you can see in some places in the galaxy where certain processes like these ones at the very beginning are still forming matter and different elements of the periodic table. And in fact, this is what is also composing, ourselves. So let's look what is the sun, a star. This star, what is happening? Let's look to what is happening to the sun. As you know well, there are responsive fusions. So there is a key process which is happening in the center of the sun, which is giving us, the process to which thanks to that we exist. We have the Earth where we can live. So, and that is, the conversion of 4 protons into helium plus something else. What is this plus something else? This plus something else is neutrinos. So this strange particle, which even if they are produced at the center of the sun, they have almost no interaction. We can even have an idea of how the sun is done if we are able to observe these neutrinos. It also produces positrons. Positrons is antimatter, it's not matter, it's antimatter. So you see how many things are produced to live ourselves, and we need all these particles to exist. And then there is energy, and this is the energy, the light that we receive every day when we get up. So in fact, the sun loses a mass, which is at the rate of 5 million tons per second. So you know well that at some moment the sun will have no more fuel and then it will explode, right? And what is the law of this reaction? This reaction is following what is called the weak force. And the weak force, one thing we have has a value which is just correct. So if it would be stronger, the universe, would be unstable. We would not exist. If it would be weaker, the sun would not radiate. So we also would not exist. So it has its right value. Why? And how do we understand the weak force? And for that to understand this weak force, which is happening, in the sun, we need accelerators. It's the only way today we have. But also you can study it on some other stuff, but mainly comes from accelerators, and the big development of the weak force of the knowledge is done in accelerators. So that was started at LEP, as Gaston was saying, in the 90s. And I think that LEP was really the accelerator that has discovered the standard model. In fact, really has built all the bricks of the model, and many of the measurements are still the ones which are used to really confront and to make the contour of the force, and also LEC. But even if it is quite some time that we are studying this weak force, the weak force still has many mysteries which we still don't understand. As you know, also at LEC, Atlas and CMS, in 2012, already 12 years ago, discovered the Higgs particle, which is one of the basic pieces of the standard model. And you see here there was some T-shirt which say, young people will say, I found a new particle. But you don't know what was happening in front was it, and I didn't get any money. Nobody paid. Okay, but that is. So the Higgs particle, what is doing the Higgs particle? Why is it so important? Because the Higgs particle, what does is to give mass to elementary particles. And how it does it? It is a kind of to have a view how the Higgs particle, there is a Higgs field all over the universe, which, particles, when they traverse this field, like a kind of friction, interaction with it, right? So it's a new interaction, you have to say. Then they acquire the mass. So a particle which interacts not too much has, more mass, like an electron. And a particle which has a much mass has much interaction. And the particles which have no mass have no interaction with this, like the photon. So that is a view of what the Higgs boson is doing. So then, what is the picture when we try to understand what the universe is that the detectors or the elements in which we use to observe this universe, we use telescopes with a big range. But if we really want to understand the first moments of the universe, the telescopes nowadays cannot really do too much. And then you can do it by accelerators. Accelerators are the only possibility in which you can get close to this magic moment in which the universe was created. So, and how the accelerators do that is not because they observe this moment. What they do is to recreate the conditions that we understand were happening at that moment. This means high intensity of energy. So that is what we try and do an accelerator. Accelerators by themselves, as I will also refer in one of the slides, the absolute amount of energy is low, but when you really see it, how it is, the density in the space is huge. And what they do is to recreate each time there is an interaction, a mini Big Bang, where we then can reproduce particles which could have the properties of them. So it's a kind of, I don't know if you if you were a fan of aesthetics. I think maybe for the young people they even don't know who aesthetic was, but for us, I think aesthetic was important. It's important in our life. Right. So, what is the standard model? The standard model then has, let's say, three main pillars, which is the particles themselves, okay? All these, what we call these elementary particles, the interactions, which is how these particles talk each other, and the symmetry, where it is reflected by the existence of this Higgs particle. Right? So these are the main blocks of this standard model. So from the particles, you know that there are three families, which are essentially in two species, which we call leptons and quarks, right? And one thing which is important to say is that these three families are somehow a kind of copy one of each other, and the main difference is their mass. So why the universe should have this copy with a difference only of the mass, and also the fact that only one of the families is, makes particles which are stable. So the other two, nowadays, essentially in the universe, unless in very specific places, they do not exist. We have to recreate them artificially in our labs or in our accelerators. But they were at the moment of the universe, the creating of the universe. So what has been the role? Why they were there? Why nature? Nature is always trying to minimize the energy, right? Why nature has created additional families? What has been their role in the building of the universe? So these are the things we don't know exactly, but these are the things that we try to understand and get. So on the fundamental interactions at the At the scale of the elementary particles, you know, there are four main interactions: the magnetic, the weak, the strong, and the gravity. At present, our standard model only can, you know, its standard model only uses these three interactions. But at some moment, we know that we should also integrate the gravity between these particles, and that is not yet has not been yet possible. So that is also another front of research on how all the whole picture makes sense. So let me then come back now. You know why this standard model is like it is. So maybe you know who Averroes was. Averroes was, you know, at that time this type of people who were, you know, philosophers, mathematicians, doctors, everybody, and he was, you know, he was Arab, so he was living in Cordoba, right? And he created a school which the main message was, in nature nothing is superfluous. So you know, there is always a reason. But
maybe he was wrong.
Maybe that's well. But
these extra families of particles.
Sí.
Maybe. But in any case,
Ha empezado ya, es que ha mandado algo mal Jorge.
María Dolores, ¿puedes cerrar el micro, por favor?
Sí.
Vemos aquí, gracias.
Sí. Espera un segundo.
In fact, now there is a current of in physics which are really saying that things happen as a kind of evolution without why.
This is why.
But I think that by asking ourselves the question why, we can progress. The other way is much more difficult to really. But yeah, okay, that's a philosophy.
It's like in evolution, there are things that are superfluous.
Well, not superfluous. At the end, if they are there, there is a reason, which is the most economical for the nature to keep it and to survive. No? Yeah. But yes, okay. Anyway, I build it. Ask you why. I build it already. So then here we look, for instance, the value of the masses of the particles. Yeah, you see that the range is extremely huge. You know? So there are, if you look here, you know, there are many, you know, powers of 10, you know, difference between the different masses, or what we call elementary particles. And in fact, you know, if we consider the heaviest particle, which is the top quark, which we consider it an elementary particle, is as heavy as a gold atom. And we know a gold atom, how complex it can be. And then there is a particle, which we call it elementary, which has its mass. So why that should happen? Before I go to the next slide, also I just want to say something which is the mass of you know, hadrons. I mean, what is the mass of the hadron, right? So the mass of the hadron has nothing to do with the weak interaction or the Higgs, because it is due to the strong interaction, which is the interaction which, you know, rules the quark themselves and with the group. So the mass of the proton, you know, has to do in the sense that these particles have this mass due to the Higgs, but then the main part of the mass of a proton is due to the strong interaction. And then, can we imagine a universe with different values of these particle masses? We have seen that they are very different one each other, and there is no reason why they have these values. We should have these values. But then let's make the question: what would happen if we change these values just a little? So, for instance, let's imagine, you know that the quarks UD, as you know, as I look here, so the difference is extremely small. But could they be different? Okay. If they could be different, let's imagine a range in which the neutron, which is made of quarks UTP, and the proton is UUD. So if the masses would be a bit different, maybe, then we could have, a neutron which could be lighter than a proton. What would happen then? That is that the proton would not be stable. If it would not be stable, nothing that we know from the elements would stay today. So they are small, we don't know why, but they are essential, the values they have. The electron mass is very small, but it's not zero. If it would be zero, they would never be trapped by the nucleus, and they would never form atoms. So we would have no atoms, right? So are there reasons for this? Maybe, or maybe not. But it is strange. And yes, so the answer is certainly, they could have different values, but our universe will not exist. That is for sure. So, and we thank this, at least for now, for the Higgs boson. We exist thanks to the Higgs. So, matter, antimatter. This is another big question that we as a particle physicists we still are exploring and trying to understand. So we know essentially from all our experiments in our labs that the production goes one-to-one, and the annihilation also goes one-to-one. But obviously in our universe there is more matter than antimatter, otherwise we would not exist. So at some moment there should be, an unbalance, something that produced a bit more matter than antimatter is. I think it's 2 parts in 100 billion. So, have you seen the picture of angels and demons? So you see, how it goes, no? Right? That they have a small part of antimatter, which is, in the barrel in a place in which it is suspended in the vacuum and so on, so not to touch the walls, and and then they have a battery which is keeping the antimatter there, right? And what is correct in the picture is that the moment that the battery could fail, then it will touch one of the walls, and then everything will explode, and will explode a lot. And but I think that the people who were really writing on the film I think they thought a lot, but they didn't realize that building antimatter is the most expensive thing you can do nowadays in the world. So to produce 1 milligram, it is more than $62 billion dollars. No? So you would need all the budget of the United States to just make it less than a gram, or much less than a gram. So then the main thing is how such a big budget could scale the director of CERN. No? That is the big question that they didn't realize. Okay, so this so we know, as I said, that this unbalance between matter and antimatter that we need is 2 in 1,000 million. And there we don't know exactly what is really producing such effect. So it could be that it is the role of the 2 families of which are heavier, and there are probably certain clues which go in this direction, but also could be the Higgs. This is an open question of our field, which are still being investigated. Okay, so now we go to the instruments. No? What are the instruments that we use to observe all this physics? And these are detectors, and there are accelerators. Detectors are the ones which have the role of giving us information on what kind of particle, energy, momentum, nature of these particles. And the accelerators are the ones which are able to produce the energy we need to recreate these conditions of Fermi universe. So then let me remind also this sentence by Freeman Dyson. says no directions desired are launched by new tools much more often than by new concepts. The effect of a concept-driven revolution is to explain all things in new ways. The effect of a tool-driven revolution is to discover new things that have to be explained. And accelerators. Well, I am here in the field, so you know more of accelerators than me, but let me just take the opportunity to say, you know very well, it's a powerful and complex tool, right? Which they concentrate energy in a extremely small space. The actors of the accelerators is very multidisciplinary, so it involves accelerator physics, engineers, computing, so it's really something which is very needs a lot of expertise from different areas and fields. And what but it is a highly technological field, and is booming. I think that each time we discover new applications of accelerators everywhere and for many applications. So the original idea of the accelerator was by Gustav Ising in 1924, which was then implemented by Ron Withrow in 1927. But the first accelerator, which was a cyclotron, was built up by Ernest Lawrence at Berkeley, and was able to produce proton 1.1 MeV. So here you see a picture from the 56, where the first accelerator at CERN was built, and here you see that they were transporting it by on the road. So that was really a spectacle. Really, people there saying, "What is this?" Yeah, that's just to have some picture of energy which we can really concentrate on accelerators. So here is just a table, but again, better than me all these figures, right? So if you really compare LAC with a higher speed train, right? So the total amount of energy is very different. It's 14 orders of magnitude less what you have in the accelerator. But when you really concentrated energy, per meter, then the energy that you have in an accelerator, right, is 27 orders of magnitude higher than what we really are able to produce in one of these. So, and what can we do with such density of energy? Yeah? So we can do particle physics, nuclear physics. We can study fundamental constituents of matter. We can generate secondary beams of X-rays and neutrons, which are also very useful for techniques for advancing images. And then we have protons and ion beams, which can penetrate and deposit energy, which then allows us to study in-depth material and biological tissues. Well, again, you know very well, these different ranges of energy allow us to also different techniques. So from security, industry, medicine, synchrotron sources, and collider for particle physics, which is at the limit of the highest energy. The main instruments for an accelerator are electrical fields, which accelerate, and magnetic fields, which guide the trajectory. So in a sense, our accelerator is composed by is very complex. It really needs a lot of very detailed instruments from the very beginning to produce the source, the particles that we want to accelerate them. Then the magnets, finally, the target where we want to deliver the beam with a certain properties. All that has to be controlled, by system, and has to be contained in cooling systems. Has to be in a vacuum tubes, which really can preserve the particles of having its path with the less distorted interaction with particles. And the accelerators are also extremely precise. This is an example at lab of what happened when we were trying to measure the mass of the Z0, which is very important parameter, and then we wanted to measure it with extremely high precision. But we had an uncertainty which was systematic that we were not understanding. So we could not control the energy of the accelerator. It was really fluctuating in a way which was really limiting the accuracy of this particle. And and that took us, I think, at least 2 years to understand what was happening until it was then systematized. No? And the guilty of such uncertainty was the moon. So the tides which were produced on the moon were changing, the dimensions of the accelerator, and that was influencing the energy of the accelerator. So at the end, we could see, all these effects. We could quantify it and correct for it. But you see here, this is a day where you see, in fact, the energy of the. And before that was an uncertainty, then later it could be corrected. So it was a good way to discover the moon 100 meters below, in a tunnel below, ground. So what are the applications? Expensive, but interesting. It works. It works. So what else? Again, nowadays, I think this slide is a bit already also. Probably there are much more than 40,000 accelerators running nowadays worldwide. No, maybe we can say that in the 20th century, maybe the driving force to develop these machines have been basic science. But I think that nowadays this is not the case, and we are probably facing the paradigm where applied science is now really probably, guiding, if not the whole development, most of the development of these machines, because of their applications in photon neuroscience and hadron industry. So here you see a picture here. So for instance, this small slide, for instance, is high energy physics, and all the others, so is medicine, radiotherapy, ion implantation, industrial processing. So what is the added value still for basic science on all these developments? So, of course, in many cases, the technology, we don't have it available in the market. So we have to create technology, new technology. You cannot go to El Corte Inglés and buy, certain instruments. We have to produce by ourselves, develop maybe at the end with an industry, but we have to develop them. And that gives us the possibility on basic science to contribute also for new developments and innovation. In other circumstances, the thing is that, even if the technology exists, the conditions of running of this technology is very hard. And then it's at the limit of the specification. So it's a place in which we can test the limits of that technology. Again, on this use, basic science can contribute on the development and innovation of such machines. And others in which probably El Corte Inglés can produce these instruments, we buy it. Of course, if we can buy it, we buy it. That is for sure. So these are our chances for development, accelerator development and innovation. So again, well that in science, we contribute in nuclear physics, particle physics, biology, chemistry, pharmacy to develop, new proteins, or to understand better their properties, and also in material science. Here is the place where it knows it very well. What else? So, for instance, accelerators are used to make X-ray fluorescence, and then to really, understand and make kind of understanding profile of the picture when they were produced, or the different techniques which have been used. In industry, industry is also very wide. They use for industrial processing, even to change the color of jewels, ion implementation, security, and material processing to make them resistant to change the properties of these materials, and also for food irradiation. You know that is probably, I think in the, I don't know if here is allowed, but certainly in the US it is. And I have seen some documentals which really show that you don't need a refrigerator to keep the food if you really irradiate them before. So in environment as well. Now there have been already several tests in which that these big ships. It is said that the market and the movement and the transport by big ships is one of the most economic and less impact on the environment, but the impact is because there is a lot of this. And then there are now techniques which are being used in which all this smoke can be irradiated in a way that then I don't know what the details, but in a way that they decompose the bad elements which can pollute. And in India there are also several projects, ones which are really also big size projects, which are used to really clean the water by irradiation. And then we go to medicine, which is close to the last part of my talk. And then we have also for medical imaging, to produce of radioisotopes, the sterilization of medical material, and then all the effects and the impact on medicine, right? On X-ray, on the therapy, and the proton and ion therapy. And now then that goes to ion therapy. Then we come back now to the first moments of the universe, and then what do you see here in this picture? This is an image of a bubble chamber, which essentially is particles which are transverse in matter, and and there are big magnet fields. So the charged particles, as you see, some of them spirals. But what do you see here? You see some particles which go aligned almost as if they were not interacting, and then there are others which are trapped, right? And the ones which are trapped, in a way, somehow they are, each time they lose energy, they even lose more energy later. So this seems to be a property which has no use, or has it use? What do you think?
It has been used. Black holes trapping.
What?
Black holes trapping. Magnetic fusion is used because you get information for this energy, from this energy that is emitted by the trapped particle.
Well, sure. this is the basic idea of hadron therapy.
They are trapped.
No, the fact that they lose energy.
You get information from you.
No, because they really stopped in a place, in a mood, where others which do not release so much energy. So this is quantified, on this formula, which is called the Bethe-Bloch equation, where you can see that the release of energy, is proportional to the charge and inverse proportional to the velocity of the particle. So that means that the less velocity, or the heavier the energy it is releases more energy. And that is also quantified in what is called the Bragg peak, what does it mean? It means that, the penetration, for instance, in water, right? So for particles which have, low mass, they irradiate, so they interact with the matter very little, but they release very little energy, but in a way that they release energy everywhere. Whereas for hadrons, which are heavier and which also have charge, they release all the energy at one place, or essentially at one place. What it allows us is that, if we have a tumor which is concentrated in a region, we can only irradiate this region where the tumor is without harming the healthy tissue which is around. And that is one of the main properties of hadron therapy with respect to conventional radiotherapy. And that there are two main issues here: the velocity, the mass somehow for the same energy, and the charge. No? I always say, physics is beautiful because that really then we can understand. So, with respect to when we compare different types of hadrons, then we see, for example, this is a simulation how this kind of interaction energy is released by protons with respect to carbon. So you see that protons release some energy, whereas carbons release a lot. One can be very much direct. So there are, in this sense and in this picture, we have good news. Good news are that photons and ions make it possible to modulate the radiation, such that then we can keep the healthy tissue, without really being very much interacted. Okay, and what we know also is that ions have, even a higher efficiency, radiobiological efficiency than protons, which means that by using ions, we can gain, right? Also, I think that even for what is the immunological system, ions have a better properties and better behavior than the protons. What are the bad news from this? Is that protons and ions are more expensive, and even the protons nowadays, you can buy now machines already, which you can install in hospitals and so on. That is not the case for ions. So in a way, we have to make now, new developments and innovation in a way that we must have these new instruments, smaller, more compact, and cheaper, no? Make them maybe more democratic to be used more well. So what are the number of, this is, as I said, also growing and booming. So there are now, I think probably these numbers are already not correct, but let's take it around these numbers. So the number of operating facilities worldwide for proton therapy is a number under 13 or so, right? And there are a few ones for ions, which are mainly concentrated in Japan, also because Japan has its own way of operating. And these are new things happening in Spain, which is Spain is really joining this club. And that that in the coming years there exist two centers already, which are from private ones, and there will be 10 new more. And that was thanks to this donation at the flag. So that is where all these sites will be localized, right? And I think I took it from Forges some years ago. Really, it was not so easy to have an accelerator here in Spain, but I think this is not the case anymore. And it will not be the case. So this is Dr. Romerales, físico teórico, sorry. Cañitrón, acelerador de partículas. Okay. So here you see essentially how these techniques work. So they can, in a way that they can scan and run, because even this peak is smaller than what is the tumor, and then you can make a scan where you can really follow what is the geometry of the tumor, right? And you can modulate. And then you see here these slides, independent of the numbers, you see how the growing of the use is going for this type of therapies. So there are many ideas on how to advance on that. There's using cyclotrons, using cyclotrons as well, but also linear to develop these new techniques, right? And what may offer these linear accelerators is to have really more compact, lower cost, to have a high pulse frequency, and then really have them pulse beams, and then possibility of treating moving organs, because they can move. So here is a picture which I have taken it also from some presentations. This maybe how that development of new accelerators could go in future. And then you see that maybe we are around here where these linear accelerators are developing. And certainly probably will not be the last word, but it's the word maybe today. One of the words which could be nice to explore. And that is one of the lines that we are offering in this new initiative, which is the last part. So I just will present a bit what we are trying to do in Valencia, and we want to learn as much as we can from what you have here, because the installation at the end from the conditioning will be very similar. So this is an initiative which is developed by CSIC and CDTI, right? And it is of an investment of almost 22 million euros, and it has a duration of 55 months. We are already started. We were discussing. We are already in the 9th month. Not many changes, but this is the group of people. All of us are here. So I think it's quite an enthusiastic group, which each time will be more and more important. This, I have to say that this is an old dream in our institution, at IFIC, which has been pursued since quite some time. And it was the first pioneer on that was Professor Bernabeu. And okay, let's say that it didn't end well, but thanks to all this, we exist today with the present project and proposal. So the main objective here, I will summarize here, has two main objectives. One is, in the sense of innovation, which is why CDTI has entered in the game, which is to make an equipment which is built by industry, and it is by Spanish industry. And it will be the first time that a full accelerator will be built by Spanish industry. But let's hope it will be. It is a challenge we have to make. And it is used by what is called the public procurement. And then there is a scientific goal as well. So it will not be an accelerator that will really treat patients, because that is really is too big project. And that would never work, because it really needs an involvement. And then it covers mostly on what is research. So it's to make an installation which should be used for radiobiological and biomedical clinical aspects. Right? So here are the different phases of the project, as I just said before. These are the main initial parameters of these accelerators. It will be called carbon 6, but we are already thinking to have also other ions and the challenges to have protons as well, especially because in the first 5 years, Spain will have a lot of proton knowledge, proton needs, and I can imagine that maybe in some of the places where it will be installed, maybe they have some kind of scientific use, but I cannot imagine that the place which is used to cure patients, we can just go there with our instrument, just take it. So then probably all these kind of test facilities to understand better the working of protons and ions as a future step should be needed, and maybe not the only one, but some others as well. And then you see here the energy to start with. We wanted to be at least to reach 10 MeVs per nucleon in order to be at least useful at the first stage. But our goal is to go beyond, so at least to have 30 or 40. Well, that is some sketch how it should work, and that is the end. So I think it is, I am old, but I think I still have, I still can dream. It's like the song of Cat Stevens, no? take your time, think a lot, think of everything you got, and for you, we'll still be here tomorrow, but your dreams may not. So let's do it. And that's it. Thank you.
So we have now time for some questions or comments. First, from the people present in the room. Anton?
I've seen nice images of the universe taken by telescopes. For example,
It's not from the field, it's just to it from London.
I have that curiosity. So you can map the universe different for regions, right? In the universe. So this detector gives some signals.
The telescope.
Yeah, telescopes give some light signals. If a black hole, how do you look at a black hole? What a black hole signal comes? Means how the detector that which location you go and what is that signal? How do you know?
Well, the thing is, you don't observe them.
Yeah, that's it.
Right? But you observe the effects of the black hole.
Detector what?
And then you have one of the things why you understand that in the universe there is a black hole is by these gravitational lenses, right? And what happens is that that you have the light and you have a heavy object, which this has been observed. Then the light, just changes its path, right? And then you imagine that you have, a source of light, and then you have a star. Right? Then what happens is that the light, which is just behind the star, you see a kind of circle, right? And what you see the star. And then what happens is that sometimes in the universe, you see the circle and nothing inside. So then it says something which is very massive has deflected this light, and that is repelling. Now, for instance, there are gravitational waves. Gravitational waves have already seen these black holes because of the effect of the gravitation. So each time there is more.
Yes. Thank you for this such a nice talk, and this is very interesting topic for me. Since long, I choose a different easy way to do material science, but it's very interesting to study nuclear physics and matter antimatter thing. I always wonder why scientists always say only 4% in universe is observable, 96% is dark energy and dark matters. Means what motivate them to say this? Why this?
Well, we have Santiago there with theories, but essentially, I think this is more on astrophysics and astronomers who really made this type of calculation. But somehow they, there is this the gravitational constant, right? And then it has a certain value, and then to justify this value, you need a certain amount of matter of energy in the universe. In a certain equation, there is an equation which tells you somehow the composition. So when you try to identify what is the composition, you see that normal matter cannot explain this value at all. So you need something else. Right?
From there, this concept.
And then when you add something else, then you realize that the normal matter is only about 4% or 5% of what is the total energy of the universe. Then you say, okay, let's see if dark matter, which is dark matter is kind of black holes that you don't observe, can make it. And then these people, made their calculations, then they arrive to the conclusion that dark matter is only 20-25% of the universe. So 5% plus 25 still is not 100%. And then there's something else must exist, which is called the dark energy. And the dark energy, for instance, is used to explain nowadays. That the universe, if the universe was originated in the Big Bang explosion, right? Let's say that gravity is the interaction which is ruling this expansion of the universe. But if you imagine that gravity is what is attractive or is attractive, So if it is attractive, what do you expect? Is that at some moment it will shrink, right? And or at least the expansion will somehow show. And the present measurements, when they see the borders of the universe, they see that the galaxies each time are far away with higher velocity. So the universe expansion is accelerated. So there must be a force which is making that possible, which its nature we don't know. And that is what is called also the dark energy. So you see, we have a universe which nowadays we only understand 4%. and not completely. So there is plenty of work.
Second question is why it is too difficult to form antimatters? And this is a basic, very foolish question. If you
well, we live in a world which is everything is matter. So you have to do it. First of all, you have to isolate it, because the moment you make just a small positron, whatever is absorbed by nature, right? So then you have to keep it in an isolated way, and the only way we know how to do it is by making these interactions, because then it's one by one, one electron, one positron. So to make a 1 gram of antimatter, you can imagine, how difficult it is. So at CERN, not in LHC, but there are still some experiments which are assigned to LHC, where one of the main goals is to produce anti-hydrogen. So really to make, hydrogen, which is, an anti-proton and positron. And they have reached it, but they have reached it, in numbers that it's a few ones. So that's far from being 1 gram.
Thank you for the very nice talk. I have enjoyed it very much. I have first a practical question. As I remember properly, the first ion therapy machine was ready in the end of 50s, the beginning of 60s, something like that. When do you expect we will have ready this hadron therapy based on? Do you think it will be?
Well, as I
commercial line?
Well, this is, in Europe, I think there are 3 places.
Yeah. In other words, what are the limits? Is it very expensive, the accelerator? We need more coils, better coils?
Well, that was the idea. I mean, there are also synchrotrons, and one of the ideas is also to have them linear, because then you can play with the radio frequency and make them more complex. So I think the price of these machines nowadays, when you could build up with the present technology, we are talking about 150 million.
So you could build it, but
you could build it. In Japan, there are some of these. Then in Europe, they are tied to technological centers. So there are places in which you have also, an accelerator, PSI, Heidelberg. They produce other things, and then they have a line which is not really on a commercial way as it is for protons nowadays. So it's not an issue of the concept; it's an issue of making it cheaper and more compact. And that is the idea of our project, which is to habilitate our industry to enter also in this game and offer this possibility in the future. I can believe that in the 50s, probably to have an X-ray or some kind of machine that we can have in the hospitals. Probably people were thinking, that will never happen. That is very expensive, essentially. And now we have them in all hospitals.
Second question related to lasers. The highest acceleration ever has been got in
5,000.
Yeah, it's in a laser device. Do you think that someday we will have some?
That is fantastic. I think, in my opinion,
I think it's a question of time, because the laser technologies.
Yeah, but that's again, I'm not an expert, I am quite familiar with, because I have some contacts with people at DAISY, but they are really very much involved in developing these techniques of plasma accelerator. And, I think it's probably one of the most promising lines for the coming years to really work on that. As you said, the gain is 1,000. So, one could, of course, that would not apply, this factor could not apply fully, but imagine, we are planning for 100 kilometers accelerator, which then, in 100 meters, you could have the same gain. But the problem, and again, I think that Gaston probably knows better than me, is to really make an accelerator out of this concept. So the thing is, we need luminosity and we need energy. And it seems that for today, for plasma, it's very difficult to get both.
Also, all the lasers are pulse. Maybe for this kind of therapy, you will need some continuous acceleration.
The thing is to really make an accelerator out of that concept, which really works as this one. I find that the people are thinking more, which could be a reality, maybe not very far in future, is to make hybrid. So in which you have, starting
with your plasma,
you get your plasma, then you create this energy with already with certain energy, and then later you still use some conventional acceleration. So that probably is closer in future to be a reality. But certainly, I think this field really is developing fast. It also doesn't need big installations, so you can really do it. Still can contribute to the development with not very big infrastructures. So I think it's certainly something very nice.
Yeah, there is even in Spain a center in Salamanca. These guys very interesting. Even I propose them to create neutrons using this laser technology, which can be useful for me. And just
and then you have to focus there.
there are a lot of things to do. But
it has to start.
And my last point was related to this superfluous particle. If you think that the evolution of the universe is similar to the evolution of the life, there are a lot of experiments made by the life that are not successful. Disappear. There are a lot of species that are disappeared.
But they are not successful for a reason.
Yeah, I agree with that. But you can have some.
You must have the reason.
You can have some species, some heavy particles that are not successful because you don't need them. It's just speculative thinking.
No, but you have, of course. No, I have nothing against that argument. But first of all, we still don't understand a certain issue, which is this unbalance between matter and antimatter.
Sure.
And
this point
and you can extract some lines in which these families or these particles have an influence on them, because we have certain asymmetry. Maybe not yet enough quantity as we would need for this, but there are links which you can. This is not just that I'm not saying this is the reason. You cannot say that today. That would be a Nobel Prize if somebody could demonstrate this. But there are arguments to think that they could have some role on this. I'm not saying they have a role. I'm saying that could be possible. And also on the Higgs, there are also some models in which they can establish a link between, this asymmetry at this with the Higgs. But of course, it's not only to make the link. Is then we are scientists, we are physicists, so then we have to demonstrate that is the case. And for that, we also have to demonstrate other observations which we have not yet done successfully, but that's why we have all these experiments going on. They are really trying to understand this. And that is why at LAC, where you have one experiment, which is LACB, whose main role is working on this. but no, not yet come to the result.
Do you expect any accelerator there soon?
Well, we are working to make it. I'm not okay. I will not. Because especially
There is someone thinking.
There will be. I think we need another accelerator.
I think so.
That is for sure. Which one is not easy? It's not easy because at LEC, we had LEP. LEP, as I said, LEP discovered the standard model. Very precise predictions, and one of the predictions was, at the order of 1 TeV or less than 1 TeV, either we have a Higgs or we have something else. I would have preferred something else because it would be much more interesting. But we had the Higgs, which is in the standard. Unfortunately, today we don't have this type of determination. So we need new physics. We need many things to explain. As I said, there are still big questions which have not been answered. So we need to explore. But where and at which energy? We don't have a hint nowadays, which can tell us, if we make a new accelerator at this energy, we will find something new. We don't have this kind of precision. What we know is that we have a new ingredient now, which is the Higgs. But the Higgs probably is a window to new physics and is a window to be explored. We have produced the Higgs. We know how now to produce, how to make Higgs. So the next machine has to be a Higgs factor, because it's the only way where I think we can learn about what new physics could be, or where we can explain these features. So it's the tool we have, and we have to use it. So sometimes in my last slide, I just, I put just one of these lights on the traffic light, where it's light and then nothing, everything is dark. And there is a joke. You know the joke. Because if I have my kids, if they are there, I will not find them.
No, it's clear because up to now we have been guided by
the
standard model. Now, yes, up to now we have been guided by the standard model. But now we have to look for new systems.
What it was is that any deviation from the standard model, we know is very small. It cannot be big because that is, so it has to be small. So the new machine has to be able, to reach this accuracy.
Any other question from people present in the room or from people connected to the meeting online?
Nobody has it.
Just speak up if anybody from the audience would like to make any question. Open your microphone and ask. No? Okay. And I just wanted to add a final question, if I may. The project you explained will go for this first phase with the carbon beams, which would be in the 100 MeV regime, 120. You said 10 MeV per. So about 100 MeV. The way you can imagine a facility of this type, you would be focused completely on radiobiology, or you would be considering to do other things?
Well, we have been talking about that. So our aim would be to cover, I think one of the main ways we understood was a correct way to go was to go more sequentially than in parallel. So go step by step, get something working, and then go to the next step in a way which can be affordable. So, of course, all these things are our dreams, as you said. But we, to have a line which would be used to radiobiology, another line which could be for materials because these things are very useful. Another line which to develop detectors. So we have to develop, new cavities or new instruments. So that should be. So all that is in our mine, but that costs money, that costs time. And I think what is more relevant now is to start. So we have a project which is defined. It's defined on a radiobiological use, and that is what I think we have to guarantee at the first stage. Of course, we in parallel we are already thinking on all these other uses, to increase the energy, to use other ions, and then to make new lines, and then how to instrument all these lines in a way which, as we have been discussing, being more automatic as possible, because we see and we suffer very much from manual things, especially on biology. In fact, we have started a small group, mainly not to really make an impact on radiobiology, but to learn what it will be needed for radiobiological studies in this facility by ourselves. But we don't deny making an impact if it's possible, but that is not the main.
Okay, I think then we can finish the seminar. Thanks very much again.
Thank you.